So last we left off at the dihedral group and the notion of a group action. Now let's go to what a permutation is. So a dihedral group already introduces you to this notion of viewing a group as basically a bunch of functions with the function composition as the operation. And every single group can be thought of it like that. So let's go to something that is sort of just a very simplified way of looking at every group. So we're going to look at the permutations of a set. So consider a set of elements, and for simplicity I'm just going to think of them like numbers. I don't know. So consider S to be like 1, 2, 3 all the way till n, and consider any function, any bijective function f that sends elements from S to S, obviously, such that f is bijective. Then f is a permutation on S, right? Yes, and then the set of all f. So this f is bijective thing. I can also sort of write it slightly in a shorter notation as such that there exists f inverse. Yes, it's a function. It has an inverse, then it's a bijection, obviously, right? So the set of all such f sending elements from S to S such that there exists its inverse, as in to say it's bijective. That's the permutation group on this set, and this set is just like the n numbers, so it's Sn, right? But in general, say you had a set X of some abstract objects like object 1, object 2, whatever. Then the permutation on this set is like S sub X, and so that's the functions which send from X to X such that there exists an F inverse. Right. Now every other group is essentially made up of permutations on some set, right? So it's made up of elements which are also in this Sx thing. So if group G acts on the set X, then for every so for all small g element in G, what's going to happen is that G is also going to be there in S sub X. So S sub X is called the symmetric group in X, right? Yeah. Okay. So let's go and try to think about just permutations, the functions themselves in slightly more detail. So let's consider one of the easiest sort of permutations, which is like, you just rotate the whole set around. So like, so say you have these elements 1, 2, 3, 4 till n, and you map it like this: 1 gets sent to 2, 2 gets sent to 3, and 3 gets sent to 4, and then maybe like you send 4 to 1, then you leave everything else the same. So in a sense, what we are doing is that we are cycling these elements, right? And so that's what we call a cycle. So we write it like this. We write it as 1 gets sent to 2, 2 gets, so 2, this element, it gets sent to 3, and 3 gets sent to 4, but 4 once again gets sent to 1. So we can close this cycle, right? You actually don't write like this, you don't have this stuff, but whatever. And in my, so it's just for my preference, I like to write it like this sometimes, but never mind. I think parentheses is good. So so this is this cycle is a permutation. Now if you think about it, every single permutation is just a bunch of cycles, really. Yeah, so here's how you do it. Like, you are given a random permutation. What you go around doing to form this thing is, you first ask, where is 1 sent to? So if it's sent to 2, you write 2. Maybe then you ask, what's 2 sent to? And maybe it's sent to 4, and so you say, okay, it's sent to 4. What's 4 sent to? So they might say, okay, 4 is sent to 5, and then you say what's 5 sent to, and they say 5 is sent to 1, and if it's sent to 1 you close this cycle. Alright, cool. Then you ask what's 3 sent to, because notice that 3 wasn't there, right? And then you open a new cycle essentially. So they say okay, 3 is sent to 6, so you say okay, what's 6 sent to? 6 is sent to 8, and then what's 8 sent to? It's sent to 3. Cool, close the cycle, and then go for the next one. So 3 is already there, 4 is already there, 5 is already there, 6 is already there, 7 is not there. So then you ask what's 7 sent to, and then say okay, 7 is not sent to anything, it's just remains like that. So you close the cycle like that, or if you prefer you can probably not even write it. And so this denotes the same thing as this function. So what it's doing, so I'm just gonna write 1 2 3 4 5 6 7 8, and then everything below that is like just remains same, so I'm not going to do anything with that. So what's happening is that 1 is sent to 2, but then this 2 is sent to 4. I know it's sort of an abuse of the mapping to write like this, but essentially 2 is sent to 4, yeah. Then 4 is sent to 5, 3, and then once again 5 is sent to 1, right? So that completes this cycle. Then so what you can sort of do is sort out everything that was in this cycle, and so you just write 1 2 4 and 5, and then all of the other stuff like 3 6 7 and 8. Heck, even 7 is like not in the next cycle, so I'm going to write like 8 and 7 like this. So this is one part, and this is one part, and this is one part, right? So 1 2 4 5 over here. So 1 is sent to 2 is sent to 4, 4 is sent to 5, 5 is sent to 1, right? So that completes one part of this function. Then you have 3 6 and 8. So 3 is sent to 6, 6 is sent to 8, 8 is sent to 3, and that completes another one. So just with rearrangement you can change these sort of. So you can think of each function as made up of cycles, right? And then 7 just goes to 7s, obviously. Now what's essentially happening is that 1 can never essentially be sent to, let's say, 3, right? So the orbit of 1, as in everything that 1 can potentially be sent to with like if you just keep applying this function, right, over and over and over again, yeah, then 1 can only be sent to 1 2 3 1 2 4 and 5, right? So like if you were thinking of just applying this function over and over again, the orbit of 1, or more like all the elements that 1 can reach, that's just going to be 1 2 4 and 5, and similarly the orbit of 3 is going to be 3 6 and 8. Now I'm using the word orbit, and it's going to be obvious what this like really means a few videos down the line. But for any group G, an orbit is an orbit G dot A is essentially all the elements that A can reach, right? So in this case the orbit of A is with the group let's call this permutation as P, is with the group P square and so on, like whatever identity, obviously, right? With this group, obviously with the function composition operator applied on A, right, that gives you the orbit of A. Okay, cool. But that's not really important right now, because we're just thinking of the like individual elements themselves, like permutations as functions and nothing more. We're not thinking of groups right now, so you can completely forget what I just said about orbits. It doesn't really matter, but eventually you'll see like what this is really. Okay, so I think now we have like a good grasp on what this cyclic notation really means and what it does. Let's try to see how to multiply two permutations written in the cyclic notation. So you already know how to multiply two functions together as maps, right? And so this shouldn't be too hard. So let's try to multiply, I don't know, maybe this thing 1 2, and then you got like 3 4 or something. Multiply this thing with 1 2 3. So once again, as functions go, you first apply this function to the object and then you apply this function, right? It's function composition we are doing. So what's this doing? It's sending 1 to 2, but then this thing sends 2 to 1. So 1 is actually it's just sent to itself, right? Similarly, 2 is sent to 3, and then 3 is sent to 4. So essentially 2 is sent to 4. What about 4 itself? Well, this doesn't do anything to 4, so it just remains like that. But 4 is sent to 3, right? And so in effect 4 is sent to 3. Then let's just see what happens. 3, so 3 is sent to 1 and 1 is sent to 2, so 3 is sent to 2, and so we can close this cycle, right? Okay, so 1 2 3 and 4 are figured out. What about 5 and 6 and 7? That they're just going to stay the way they are. Like this keeps it just as it, and this keeps them just as is. So yeah, so this whole multiplication just boils down to this. And so 1 is just the way it is, like we can kind of forget this, and so it just becomes this cycle 2 4 3, which is like way simpler to imagine rather than this complicated thing, right? Yeah. So that's on cyclic notation of permutations and what permutations are in group theory. And so I'll see you guys in the next video.